Hello, my friends. Moving on with predictive models, I want to talk about these four main machine learning models that we can use to build predictive models. So, decision trees, random forests, gradient boosting, and neural networks. So, decision trees. The idea is to split data according to some rules or criteria that you define, and then keep doing that. Split data, split data, split data until you manage to develop kind of a group with certain characteristics. So if you find another individual, you can kind of group that individual according to the groups that you developed by using these decision trees. So this image kind of represents what it is. So we have a first data, we have data here, and then you divide into two criteria, and then you divide again into two different criteria until you get, in this case, you got like four different groups, and you can do naturally you can do with way more groups, and you have to define a criteria. So they call these those conditions nodes and leaves. That's why they say trees, because it would look like the top of a tree, like the main leaf and then the other leaves, like kind of looks like a pine tree. That's the idea. That's why it's called decision tree. The advantage is that it's easy to interpret and it handles non-linearities and interactions. And the limitations is that it's unstable and small data changes can alter completely the tree, which is prone to overfitting. So if I take a criteria to define the two groups, and then let's say that above a certain grade it's group A, below a certain grade it's group B, and then if I change this criteria to, I don't know, like 10% to one side or 10% to the other side, it might completely change the model. So it's not a very stable model, and because of this, mathematicians and scientists developed the random forest, which is the idea of combining multiple models of decision trees. So it says here the ensemble method, combining multiple methods of the decision trees. So you do one decision tree and other decision trees, and then you combine them. Using computational simulation, you can produce many decision trees. That's why it's called a forest, because it's got many trees. And the idea is to reduce overfitting of individual trees. It's got higher accuracy, and it can handle more variables. So random forest is kind of the next step of decision trees, which is obviously we use a lot of computational methods to develop this and reduce error. The other method is the gradient boosting, or it's got a variation, the XG boosting or light G gradient boosting. And the idea is to build trees sequentially. And for each new tree, you try to correct the errors of the last tree. So you come up with the criteria, and then you build the tree. And then you see that you compare that tree to the real results. And then you do it again and do it again. And then you refine the criteria to create the divisions, the little boxes that go down the tree. And then you do many of those over and over again until you find a model that works, that performs better. The advantage is that it's usually is the highest performing model. If it's well tuned, it tends to reduce error and it presents a good model. And the limitation is that it's harder to interpret. When you deal with this type of method, it's harder to interpret. And the last one I want to talk about is neural networks. The idea is to create neurons combined by layers. It's good for unstructured data if you're dealing with images and text. The limitation is the same for most machine learning methods, which is this black box is hard to interpret. And it requires large amounts of data and computational power to learn, to perform. And you can't really tell why one thing is causing the other. But it works to create a model to predict the next value. So it's good to get a good prediction model, but you don't really know what's going on inside of there. So it's hard for conclusions dealing with real logic, but they tend to work better if you're trying to create a model to predict the next value. I'm not going to spend too much time explaining the logic behind it, because each of those models are very complicated. I would spend hours to go through the logic behind all of them. I'm going to show you how to use them, which I think is far more useful using LLM models, the AI models that are revolutionizing society nowadays. So let me show you. Going back to the model that we presented in our previous video, the idea of predicting the number of electric cars that will be sold in the United States for the next 3 years, we did the econometric methods first, and then I ran the machine learning methods. By the way, it's important to say that machine learning is not like what AI does today. What we call machine learning in predictive models and data analysis is not the same thing as in AI, that you just get a lot of documents, texts, and asks, and for some reason the application works to get you information that you want, text, those things. Machine learning in econometrics and data science, it's simply a model. It works like an algorithm, a series of tasks performed in a certain sequence that bring you a result. It's a mathematical result. It's not that the tool is going to learn itself. Machine learning models in data science, they don't learn by themselves. You can't, like an artificial intelligence model that we have today, you can't simply throw in data and expect something to come out. Present me a good result. It doesn't work like this. The AI models, they do this using the methodologies. You can use them to run methodologies that are going to present you good models. But that's what AI does. The large language models do, and not what machine learning in data science do. The methods that I'm presenting, they don't work this way. So LLM models, in my opinion, are way more evolved than what we used to call, than what we called machine learning in data science. So going back to Google Gemini, I ran this prompt. So create a predicting model based on the data provided by the CSV file that I uploaded using gradient boosting machine, the methodology XGBoost, which is the methodology that Gemini suggested. And show me the predicted numbers of cars sold in the United States for the next 3 years, robustness tests, and all those things. It says, of course, as requested, I have calculated it. And it presents, now when you ask those informations, it's got the prompts on the left and the results on the right. And then he came up with this XGBoost predictive model for United States electric vehicle sales between 2025 2027. It's got the forecast, and then it says model selection and specification, why XBoost, why it works, and the series that you used, and the model coefficients, and then it presents the expected value of sales for each year, well, 2025, 26, 27, based on 2011, 2024 data set. Because the sales of electric vehicles has a log behavior, it tends to go exponentially. It's hard to say that it's going to keep on exponentially, probably not. But according to the behavior of this data so far, this is what it predicted. So it predicted 2 million cars 2025, a bit more than 2.5 million 26, and a bit more than 3 million in 2027, and it's got this growth here. And then it says XGBoost model predicts slightly more aggressive growth than the regression model, and it's got some robustness and validation tests, and explains the robustness tests and what are the results interpretation. And then I did the same thing in Claude, which is very good, but it didn't present me the results here. It came up with some sort of error because I'm using the non-paid version. Although I'm thinking about subscribing it because it's really good. So the model coefficients and feature importance brought coefficients for each of the variables that we were using, and it even explains why they're used. And it's got a slight difference from the Google Gemini, because it says here that the most important one is charging infrastructure, and for Gemini it was the second one, and the first one for Gemini was EV models available. And EV models available is the second one for Claude. And then it says other types of information, and it brings here in the end a 3-year predictions sales. And then 2025, 2.35 million, 2.84 million, 3.22. And the models here said 2,200,000, 265, 313, 3,130,000 cars. So it's got a slight difference to 210, 2650, and here says 235, 284, 322. So it doesn't bring exactly the same results. And it has the robustness tests and says that they all passed. And it brings insights and models and how it was built. If I had the paid version of Claude, I would keep on asking for new information and how to solve that, because it presents much better results than Google Gemini. Google Gemini apparently is not made for this type of calculation, to run those econometric tests and models, and Claude apparently is made for this. So it brings much more interesting results, much better explained, and the suggestions to me seemed much more reliable and interesting. These are the ways that I suggest you to perform machine learning analysis without having to learn too much on softwares. Obviously, you can do this using Python, R, Stata. They provide tools for machine learning, but it's not even close to the easiness to use this one, to use the LLM models. They make it so much easier. What you can do is use LLM models to create codes that you can apply in Python, in R, but it will probably be much harder to use Python language, which is the one I would recommend if you're dealing with large data sets. It's much harder to use Python to program it to run those models than to use a large language model, or in provided with the information, the data, and asks the large language model to run a test to see what happens. So this is what I wanted to show you on machine learning for predictive models. I think it works. Apparently it works. And it's, I don't know, 1% of the work that you would have to do it yourself using a software. That's what I wanted to present you, and I hope I see you in our next videos.